Humanity has spent thousands of years looking at the sky as if it were a personal challenge. First came the pyramids, then the cathedrals, then steel towers and glass skyscrapers, until we reached the point where entire cities began competing to see who could build the tallest structure on Earth. Today, when someone looks at the Burj Khalifa, it feels like engineering has already won. The building pierces the clouds, dominates the horizon, and makes anyone standing below it feel incredibly small. But there is a far more terrifying question hidden behind that achievement. What if humanity decided to keep going? What if tomorrow a country announced a tower 2 kilometers tall, or 5, or even 10 kilometers high? In theory, it sounds simple. Just build a wider base, use more steel, more concrete, and more money. But at extreme heights, reality begins to behave differently. Wind stops being just wind and becomes a destructive force capable of tearing entire structures apart. Weight stops being a detail and starts crushing the building itself. The taller a structure grows, the more it tries to sink the planet beneath its own mass. At first, engineers believed the solution was simple: increase the strength of materials. Reinforced concrete revolutionized the 20th century and allowed cities like New York City and Chicago to rise toward the sky. But there is a cruel detail most people never realize. The taller a building becomes, the more of it exists only to support its own weight. In gigantic skyscrapers, the lower floors are constantly crushed beneath thousands of tons of pressure day and night. At a certain point, adding more height stops being useful because the structure spends most of its energy simply trying to remain standing. It becomes almost like a living organism using all of its strength just to breathe. And then, another invisible enemy appears: atmospheric wind. At extreme altitudes, air currents reach violent speeds and create microscopic oscillations that spread through the entire structure. A building several kilometers tall does not sway a few centimeters. It can oscillate by entire meters. People at the top could experience dizziness, nausea, and disorientation simply because the structure would constantly be moving. And there is something even worse. When the wind matches the natural frequency of the building, a phenomenon called resonance appears. It is the same principle capable of destroying entire bridges. At that moment, the structure begins amplifying its own movement until collapse becomes inevitable. It was exactly this fear that made countless experts believe humanity would never surpass the 1-kilometer mark. But the real problem had not even begun yet, because there is a far more dangerous enemy waiting above the clouds: the human body itself. There comes a point where a building stops functioning like a normal building and begins behaving like an artificial ecosystem. And this happens long before we ever reach 5 kilometers in height. When engineers began studying megatowers capable of rising beyond the clouds, they quickly realized the problem was not simply keeping the structure standing. The real challenge was keeping human beings alive inside it. A gigantic skyscraper does not only need to transport people, it must move water, energy, oxygen, food, waste, sewage, cooling systems, and thousands of tons of infrastructure operating non-stop. In a tower several kilometers tall, water becomes a brutal enemy. Pumping water to such heights requires pressures so extreme that ordinary pipes would simply explode. Elevators also become terrifyingly problematic. Modern elevators already reach incredible speeds, but inside a 5 or 10 kilometer tower, even that would not be enough. The journey to the top could take dozens of minutes. Worse still, the human body would begin suffering during the ascent. Rapid pressure changes would affect hearing, breathing, and even blood circulation. At extreme heights, the building would need to function like a permanently pressurized aircraft. Any failure in a window, any structural crack, or any sudden decompression could transform entire floors into fatal zones within minutes. For the first time in history, architects began realizing something disturbing. Gigantic buildings might not simply be difficult to construct. They might be biologically hostile to human beings themselves. Even so, that did not stop some countries from imagining absurd projects. By the late 20th century, Japan faced a desperate problem. The population was growing rapidly, urban space was disappearing, and entire cities were beginning to collapse under overcrowding. That was when proposals emerged that shocked the engineering world. One imagined a megastructure nearly 4 kilometers tall, capable of housing more than 1 million people inside a single building. Another was even more extreme: a 10-kilometer tower functioning as a complete vertical city, with hospitals, schools, parks, and internal transportation systems. These would no longer be buildings. They would be artificial mountains built by humanity. But there was a terrifying detail hidden inside these concepts. To support a structure of such magnitude, the base would need to stretch for kilometers in every direction. The building would become so heavy that it could slowly deform the ground beneath it. Yes, a structure could literally begin sinking Earth's crust. In seismic regions, the danger would become even worse. A moderate earthquake could generate massive oscillations at the top of the structure, triggering movements capable of destroying thousands of floors in sequence. Then, another almost unbelievable concern appeared: climate. Scientists began debating whether a megatower of this scale could alter local winds, create permanent shadows over entire cities, and even change rainfall patterns in surrounding regions. For the first time, a single building was beginning to threaten the balance of the environment around it. Even with all these problems, engineers still believed there might be a solution hidden in an unlikely place: microscopic materials so strong they could completely redefine the limits of human construction. That was when science discovered something that looked like it came directly from the future, a material so thin it almost disappeared before human eyes, yet so strong it could withstand enormous forces without breaking. The discovery came from an experiment that initially seemed ridiculous. Two scientists began peeling microscopic layers of graphite using ordinary adhesive tape. The goal appeared trivial, but eventually they reached a sheet only 1 atom thick. It was graphene. What shocked scientists was its strength. In laboratory tests, graphene proved hundreds of times stronger than steel, while remaining incredibly light. Soon after, researchers began transforming these sheets into microscopic cylinders known as carbon nanotubes. Then a dangerous idea emerged. If these nanotubes were so strong, perhaps structures far beyond anything previously imagined could become possible. For the first time, engineers seriously considered buildings tens of kilometers tall. The internet exploded with theories. Some claimed future cities would be made entirely of graphene, invisible, ultralight, and nearly indestructible. It seemed humanity had finally discovered a material capable of defeating physics itself. But reality hid a cruel detail. There is a massive difference between creating something microscopic in a laboratory and building colossal structures in the real world. The problem with carbon nanotubes is not their individual strength. The problem appears when scientists try to combine billions of them into something large. At microscopic scale, they are incredibly strong. But when researchers attempt to turn them into giant beams or cables, failures begin appearing. Fibers slide against one another, tiny imperfections multiply, and the overall strength collapses dramatically. And there is another brutal obstacle: cost. Producing even small amounts of nanotubes already requires advanced laboratories and extremely expensive processes. Building kilometers of structural material with this technology would cost trillions of dollars. Even so, some researchers kept pushing the idea further. And that was when a proposal appeared so absurd that many scientists initially thought it was a joke. Instead of building a tower supported by enormous walls, why not create a structure supported by movement itself? The concept became known as a space fountain. The idea sounded simple only on paper. A gigantic structure would launch magnetic capsules upward at incredible speeds through a vertical column. At the top, electromagnetic systems would slow the capsules down, transferring momentum to support the tower against gravity. In other words, the building would partially float thanks to the constant motion of these particles. It sounded like science fiction, but the calculations revealed something terrifying. Theoretically, it could work, yet there was a horrifying flaw hidden inside the idea. The entire structure would depend on continuous power operating without interruption, because if the system shut down for even a few minutes, the largest structure in human history would come crashing down from the sky. But perhaps the true limit is not engineering alone. Perhaps it is the human body itself. There is a point in Earth's atmosphere where the environment slowly becomes incompatible with life, and the higher a structure rises, the deeper it enters that hostile zone. Pilots and mountaineers have known this problem for decades. At extreme altitudes, the air still contains oxygen, but atmospheric pressure drops so dramatically that human lungs can no longer absorb oxygen efficiently. The brain begins failing before the victim even realizes it. The symptoms are deceptive. First comes dizziness, then euphoria. Many victims begin smiling moments before losing consciousness. Inside a tower several kilometers tall, the upper floors would need to function almost like space stations, fully pressurized, climate-controlled, and isolated from the outside world. And the danger does not stop there. At higher altitudes, solar radiation increases dramatically. The atmospheric shield protecting humanity becomes thinner and weaker. Then there is an even more terrifying boundary known as the Armstrong limit. It is the altitude where atmospheric pressure becomes so low that liquids begin boiling at normal human body temperature. For the first time, engineers realized something deeply uncomfortable. Building a gigantic structure might not be enough. Humanity might need to create an entirely artificial environment simply to survive inside it. While some scientists tried solving these problems with futuristic pressurized systems, others began thinking in a completely different direction. What if humanity had been asking the wrong question from the very beginning? What if building upward from the ground would never truly allow humanity to reach space? That was when an old idea returned to terrify the scientific community: the space elevator. The proposal sounded absurd. A gigantic cable would be attached to a platform in geostationary orbit, roughly 36,000 kilometers above Earth. The cable would remain stretched thanks to the planet's rotation. Cabins could slowly climb the cable, carrying people and cargo without rockets. For the first time, reaching space might no longer require gigantic explosions and billions of dollars in fuel, but the concept hid almost apocalyptic dangers. A single meteor strike, piece of space debris or structural failure could sever the cable, and an object tens of thousands of kilometers long collapsing toward Earth would not simply be an accident. It would be a continental disaster. Even so, the idea of the space elevator survived for one disturbing reason. For the first time, humanity began realizing that the future of construction might no longer belong entirely to Earth itself.